Okay. Hello, everybody. Welcome in this webinar. I think that you can hear me. Okay, I have the role. I am Guido Noce. I'm the general manager in Dimac. You can interact with us using the chat in Teams. If you want, as you have seen, your microphone are not enabled to speak with us. A short introduction to this hour of webinar. We want to speak, as you know, about artificial intelligence as a solution for threat detection, for defect threat control and detect defection in thread in a quick way. Before starting with this webinar and this demo, I want only to introduce Dimac. I think that quite all of you know us. We are specialists in sorting machine that for 100% control, but we are also working a lot in and with increasing success in the SPC automation in the shop floor, so solution that can be used also in dirty and oiled environment. Today we will speak about, in particular, about quality sorting machines for 100% quality control, and we have organized a set for this work. I want to show you what we are organizing. As you can see, we have a direction for the movies here with Alan on my left. We have also Gabriele that is ready in his position, ready to speak and show us all the solution. And show us all the solution. We have only Simone Silvestri that is in his office and will help us with our with the eventual question that we have. So
Hello,
all is ready. I think that this is the moment for Alan to start to explain us something about theory. And I hope you can enjoy about this webinar. Thank you. Are you, Alan?
Hello. Can you guys hear me? Great.
Yes.
Welcome, everyone, and thank you for joining us today. In this session, we'll explore how artificial intelligence is transforming one of the most challenging areas of fastener inspection, which is thread control. All right, so let's start with the basics. Thread inspection has always been a tough nut to crack in automated quality control. And it's not just because of the geometry. Yes, we can measure things like overall length, inner and outer diameter, crest height, and crest count. Those are relatively straightforward. But what really matters to the end user is how well the thread engages, its ability to hold under load. And that depends on tightening torque. And here's the challenge. Measuring torque directly means running a full screwing and unscrewing cycle with a calibrated motor and gauge. That's slow, expensive, and simply not viable for 100% inspection. Deve competir. Okay, one sec. Okay. Lo sta facendo tu. Ali. All right. And there we are. Sorry, I didn't share my slide. Okay, so we're saying that the process is slow, expensive, and simply not viable for 100% inspection. And it's rarely used in production for that reason. So over time, the industry has developed alternatives. Some of these systems have been used for years and remain an integral part of our toolkit. Um, and not just just to clarify, they're not being retired. They're reliable, proven, and still widely deployed. But they do have blind spots, certain defects, especially surface level issues like burrs, dents, or malformed threads can slip through undetected. Um, that's where artificial intelligence comes in. So over the past years, we've introduced new AI-powered inspection systems here at Dimac. Now, let me be clear because this is important. These aren't replacements, they're enhancements. They're designed to fill in the gaps left by traditional methods and push the boundaries of what automated thread inspection can achieve. So in the next few slides, I'll walk you through both the established techniques and the newer AI-driven approaches. Each has its strengths, and together they offer a more complete, more intelligent solution to this long-lasting challenge. All right, so let's begin with one of the most traditional and reliable methods, the rolling mechanical station. This is a purely mechanical setup composed of three shaped cylindrical rollers. These rollers are positioned 120 degrees apart and gently press against the thread surface of the part. As the part rotates, the rollers follow its movement. And by tracking that movement over a full rotation, the system provides an indirect estimate of thread engagement torque without needing to fully engage the thread with a calibrated gauge. It's a smart solution. We're not measuring torque directly, but the correlation is strong, strong enough to give meaningful results. And for standard threads like M6, this setup delivers throughput of around 100 parts per minute, which is quite respectable given the complexity of what is measuring. So this type of solution gives us a solid estimate of thread torque, but it does come with a limitation, relatively low productivity. That's because we need time to rotate each part properly, and there's no way around that. So now we'll show you a short video of a machine we built for a customer equipped with this exact roller base inspection. And if Guido, if you could please share the video. All right, so as you can see here um, in this example, the thread cannot be properly engaged as it fails to screw in. This machine is in MCV1. In this case, the part is being inspected is a threaded stud provided by the customer. And here you see it pass through the mechanical thread control station, performing that control. All right. So what you've just seen here is what we call the rolling mechanical station, the setup that allows us to perform this type of torque estimation and thread engagement control. Let's shift our focus now to one of our most widely used solutions, the 360 auto trigger station. And this is a classic setup, one we've installed on many of our machines over the years. It's based on profilometric inspection, and it works like this. Uh, each part is rotated in front of a fixed camera. And here's the key. We only need a 180-degree rotation to capture the full profile of the part. That's enough to cover the entire threaded surface. And in this configuration, the software compares each part to a reference model, a master part that represents a known good thread. As you can see in the slide, the image on the top shows a damaged part, flattened crest, dents, invisible wear. The software calculates a similarity score between the inspected part and the master. In this case, the score is 0%, meaning that the part is completely non-compliant. Now, by setting a threshold, let's say to 85 or 90, percent similarity, we can automatically reject any part that falls below that line. And this allows us to catch the defect, like dents, damaged threads, or surface wear, with high reliability and minimal false positives. Now, let's talk about performance. With this technique, the more images we acquire, the greater our ability to detect defects. But there's a trade off. More images means slower throughput. So we're always balancing detection with sensitivity with production speed. Um, this method, inspection, only is visible portions of the thread and uh, relies exclusively on dimensional parameters. That means there's still a small but real risk that certain imperfections like burrs or surface debris might not go undetected. Now, for threads like in the M4 to M12 range, we typically inspect around 10 sections per part, with throughput between 120 and 200 parts per minute. The exact rate um, depends on whether we're using a tip and tail configuration or a magnetic rotation system. Um, and with that, let's take a look at a short video of one of our machines equipped with this station. And I'll have Guido please play the video for us. Okay, so in this clip, you'll see several threaded studs being inspected. What you're looking at is the software interface where the thread quality is evaluated in real time. Here we go. Um, and the next image will zoom into show more detail. Here, the system is quantifying a potential defect on the threaded surface, highlighting areas where the geometry deviates from the master. Okay, so in this setup, we're using a magnet to rotate the part that gives us a slightly higher output rate compared to mechanical tip and tail systems. And of course, the system can also perform dimensional measurements, such as outer thread diameter, pitch, and other geometric parameters. So, in conclusion, this is a fast and efficient way to check thread geometry and surface conditions, especially when speed is a priority and full torque. Simulation isn't required. Again, it's widely used across our machines and remains one of the most effective solutions for high throughput profile based thread inspection. Okay, so let's move forward to a major leap in inspection technology, the multi-camera station powered by artificial intelligence. Um, this solution was born out of a specific need, clients asking for ultra high speed inspection without stopping the part. That requirement pushed us to rethink the station design entirely. Some of you may have seen this configuration in previous presentations or on our website. It's built around a three camera configuration with lateral cameras positioned at 120-degree intervals beneath the dial. This basically allows us to inspect the thread across a full 360-degree sweep without interrupting rotation. And here's where AI makes the difference. By combining the images from all three cameras, the software performs, um, let's call it a composite analysis of the entire external surface. Um, it then classifies each part as a compliant or non-compliant based on learned patterns and defect recognition. Um, so this is not just vision, it's intelligent vision. So let's break it down. Uh, what this system can actually detect. Um, the AI is trained to identify macroscopic defects, things like dents, burrs, impurities, imperfections that are clearly visible to the human eye, but often missed by traditional systems. Um, in fact, the goal here is to simulate human perception to see what a trained operator would see, but at speeds that no human could ever match. And speaking of speed, this system can process over 2,000 images per minute, um, translating it to a throughput of roughly 700 plus parts per minute. And that's a massive jump in productivity, made possible by high performance, computing, and targeted training. Um, and to showcase this in action, we'll show a short video of one of our machines, La Mille, which translates to the 1000 in Italian, commemorating the 1000 machine we built back in April of 2024. This machine is equipped with the multi-camera AI station we're just described. And Guido, have you play the video, please? Okay, so before we wrap up the thread inspection section, there's one last alternative I like to show you, which is also powered by AI. One sec. Okay, which is also powered by AI, and this solution uses a linear camera, and it's designed for a different kind of inspection flow. And Gabriel, if you could please walk us through the step. We've prepared a small demo station here with the linear camera, just to give everyone a clear idea of how it works.
Thank you, Alan, and good morning or good afternoon to everybody, depending of which part of the world you are. Thank you for joining our webinar. And as requested by Alan, here you have an example of a linear scanning camera that take a complete scan of in the 360 degrees of the parts. If you see on the monitor, so by changing the light, I can change the parts that I can that I can see on the parts. This kind of technical, so in make a development of the 360 image of the parts, and with an artificial intelligence software allow to see some kind of defect. So maybe now Guido can show you better in the image, as you can see scratch on the thread and in the picture. And this solution can be equipped by artificial intelligence software. So I give back the words to Alan to finish his intervention.
Great. And I'm back. So let me share with you one last slide, especially for those who may not be familiar with the concept of a linear camera. So as you can see in the image, this is a slightly different type of camera. It captures a sequence of images along the entire circumference of the part. The software then reconstructs those into a single two-dimensional image, a linear representation of the full thread surface. And in the lower part of the slide, you'll see several threaded components. Above them, you can see the unwrapped thread profile of each one, almost as if the thread were to be sliced and laid flat, basically. And it's a powerful way to visualize and inspect the full geometry of the thread in a single frame. All right, and with that, I'll conclude my part of the presentation. Thank you all for your kind attention. All right, so enough talk. Let's see this technology in action. I'll hand the reins over to Gabriele, who will walk you or walk us through some of the practical real-world applications of artificial intelligence in thread inspection. Thank you all. Gabriele, take it away.
Okay. Bye again. So thank you, Alan. As I'm Gabriele. I'm from the service department. As already discussed and described by Guido and Alan, our purpose for today, the most important purpose for today, is speaking about the AI related to the thread damages. But the first important thing is for sure show you something on the machine, show you something of our technician, of our technical, sorry, but also to try to give you some answer to the most critical question and the most critical fear that our customer normally say to us when we're talking about artificial intelligence. And these two big question is how can I do to make the training, and the second, how flexible is the training. This is the two bigger topics that we want to discuss with you today. Behind me, you can see one special machine that we make for our historical customer that is designed to run at very high output rate, up to 700 parts per minute, and to show to see the damage on the thread. Okay, this machine is equipped with a 3 camera positioned at 120 degrees, and this allows to see with only one picture with every camera and without stopping the machine if there is some damage on the thread. Okay. Now I try to run the machine at high speed, around 550 parts per minute, just to show you how the machine runs. And after we reduce the speed to see what the AI software see on the image. So if there is some blob or some defect in the image. Okay. No. Okay, now you can see in the right side of the part our new PLC, that the HMI, the new HMI, and in the left of the part of the monitor you can see the image of the part. Now it's very fast and it's not so easy to understand what happened. Now we stop the machine. I reduce the speed. And I run again. Here, what you can see in the image, there is the 3 image, one for each camera. And you see, when you see the red bar, you can, part is good. And when you see the red part is bad. And when you see the green part, the green bar, the part is good. As you see in some of this image, you can see the blue blob. This is the damage that the system found now. Just to try to show you in okay, so in this case, you can see in this part that in 2 image there is some blue blob. This blue blob is detected defect on the part. So just to have another example of this. So this is another defect. So this part is damaged on the thread. So this is the function of this training that is designed, that is trained to detect this kind of defect. Now, I want to show you a little bit how to create a new training, because a very typical question from the customer is how can I do to create a new training? How can I do to take the image? How many times I need to do this? How many times I have to stop the machine for doing this procedure? And so now we try to give an answer to you. So now we simulate a new training on the machine. Here, as you can see, we can give a name. So save as and give another name of on the training. For example, we can call webinar now. We can save. Now we have the webinar training. Now what we have to do, we have to collect the images of the parts. In our software, we have our utilities. Is I'm sorry, now it's in Italian. I'm sorry, my defect, I do not put in English, but this is example acquisition, okay? Here we have a floppy disk button that allows us to enable the saving of the image. And we can also give a label as okay or not okay. This is not very, very important for the training. This is only a name, a label on the image, on the images. If you already have some defect parts divided respect to the good parts, you can do it. Otherwise, you can run the parts all together, and then we can select after what is good and what is bad. When you are ready, you can simply run the machine. And automatically all these images are saved on the machine. Now we can see here in our folder that we create webinar. We go inside, we see sample, and we can find all the image that we save. Is one for each camera, so is 3 image for every part, 1 image for each camera. And then here, if you can, it's good that you divide in 2 folders, okay and not okay parts. Otherwise, this is possible that is made by Dimac technician when we make the training. But so, for example, in this case, I open one of these parts, and you see that these parts, for example, have a defect on the thread. So these parts can be put in the not okay folder, but it's not mandatory. So we can do this, or you can do this. But this is just for explain that here we have all the image, and we can divide it for good and bad. After this, you have to send us all this image, okay, all this folder with this image, and now we start at work on the training. I ask to Alan, please, if he can show us a video, an explanation video, so to better understand what we do when we make the training on the machine. As you see, Alessio, in this video, he mark what is the defect. This operation was made for every part and for every defect that you provide us. After all this big work, we run the training. The artificial intelligence software make the algorithm, and when finish these activities, so that we can continue to see. Okay. When finish this, so we create a folder, a file, and a couple, one more, not only one file, but a little bit more. And we provide you a training folder with all these parts, and you have to take all this. Now I put an example. I take the same folder from another training, so you will have your properly training. We put training feature, and we passed everything inside of our folder. So the training it's finished, and you can run immediately with your new training. Obviously, it's possible that in the future you need maybe to add some more sample because you find a new defect, we find another defect, and this is possible to integrate on on the training. But at the moment, so machine is ready with your new training. The time that we need to make the training is depend for different factors, so number of samples, kind of defect, and other couple of things. So, but for this kind of training, for example, you can think that we need a couple of days of work to create this. So you can take the image, you can continue your work with this with your machine, with maybe another parts or something like this, and after 2 days we give you back the training, and you can automatically install, you can copy this training on the folder, and you can start with your machine. Now you put the training inside, and we can directly run machine. Okay. Okay, so more or less, this is the functioning of the training, of how we need to create a training. The second typical question that very often the people ask is, okay, I create this, but how this training can be flexible? If I have some parts similar but not the same, I can use the same training, or I have to make another training again. Now I prepare here some different samples, some for color because I have a different surface treatment, measuring different size, and also some different shapes. So as you can see in the image, the first one that you can see in the left is the parts that we use now in this moment to run the parts. Okay, so now I take one of these and we try to put it to see what happens directly on the machine if we put another part that is not exactly the same but is mostly similar. Okay, now I take another part. So this part that you see here is another M6. Okay, have more or less the same treatment. The treatment is more or less more or less the same. I put it on the machine, and we will see what the machine see. Okay. Okay. Okay, now for example, we can see that this is not the same parts that we used before, but here we see that in these parts we have defects. Now I put also a good parts of this parts just to see if the good parts is green or not. Okay, so this is a good part, and you see that in this case we have two similar parts, not exactly the same but similar, and we can use mostly the same training for reading the same part. So in this case we don't need to create another one. Now we try to put a second part on the machine. Okay, so I try to show you. So this is another. It's difficult to see, but this is another M6 part. So now you will see better. You will see better directly on the machine. But have a small particular dot on the point of the parts because it's not exactly the same of the other. Now we can see. Okay. Also here you can see that in the third image, in the lower image, you can see a blue blob. Okay, because also these parts have a small defect, and it is catched by the machine with the same training that we used before. Okay, now we put the good parts. In this case, also the good parts is detected as good with the same training. So now we see that also if this part is a little bit different because of the last parts, it's different respect the original parts that we use for create this training, we can use the same training and we can work without problem. Okay. Now we pass into a third part, another part. Okay. So this is this part that you can see here. Okay, is more or less the same of the previous parts, but is black because have a different surface treatment. Okay, in this case, what we can see what happened. Okay, also in this case, I see the defect in these parts. Now, I change a little bit the program. The training used is exactly the same. What I change a little bit this adjustment, this parameter. This adjustment allow me to change a little bit the light and help me with a different color parts to sorting to using the same training. So here we can see a situation where we have the same training but with some small adjustment that is possible to do by the operator. So it's not require a Dimac technician for do this. Now we put the bad parts. Okay, this is the good parts. Okay, and you see that he found some defect also in this good parts. So probably by reducing a little bit one of these parameter, we can adjust to accept also this these parts that normally should be off. Okay, it's also important the height of the parts, but we see a first critical things. So the color of the parts sometimes need some adjustment, but we can make with the same training. Okay. Now we change our parts. So this is a smaller part because this is an M5, little bit longer, but have more or less the same color of the previous one. Okay. Also, these parts you see that have a small defect in the point of the parts, and also this one it's possible to use with the same training. Now we try to put the one good parts without defect. Okay. You see that you see a very small defect, the defect in this area that we can adjust with the dimension of the blob to say to the machine to accept also these parts that is good, but you do not see any other kind of blob in the area. Now we can pass to another part that probably it's not easy to see with this image, but have a small cut in the end of this part. This is an M6, but it is a different shape. We put here, and then obviously we see that in this case, for sure, we need to have a new training because this part is really different than the other. And so in this case, probably it's not enough to adjust some parameter or to adjust something on the machine to use the same training, but we have to acquire the image as I make before and create a new training. Another example that I can show you is this part. This is a complete different thread. Okay, and also in this case, you see that the part is the thread is completely different, so the machine do not recognize. So when I start to have this kind of difference, I have to make another training. In the end, the last part that I show you, this one is more or less an M6, but have a completely different surface treatment. And so the reflect on the machine, for sure, it's different, and it's very difficult. Okay, so you see that the reflect of this part is completely different. So in this case, I need for sure 100% to make a new training. Okay, I mostly finished with my presentation. We hope that you have the idea a little bit more clear about the functioning on the AI, that how to make the training, how the training can be flexible. Okay, and thank you for the attention. So maybe we can see later if there is some question. I give back the words to Guido, and thank you very much.
Okay, thank you, Gabriele. This is the time for questions. You can use chat for new question for us if you want. Waiting for some question. Your microphones give some strange sounds, Gabriele, but this is not a problem. For the moment, we don't have any question. Okay, we have the first question is, but somebody has asked us if it's possible to train a part with more than one components. It's possible to use more different parts in the same training?
The question is, the answer is mostly yes. So we can training a potential one part, for example, for a crack in the head and the damage on the thread. Obviously, we have to consider that the time for process the image can increase, and so in this case, probably the speed can be reduced. But the answer at your question is yes, it's possible to train for different kind of defect in the same parts. This is the general answer. We have to check case by case to see if really it's possible to see the defect or not, but the answer is yes.
So we have a question from our friends in Brazil. The speed of 700 part per minute is currently checking only the thread characteristic of the screw. Can the other feature inspected at different station also operate at this speed? Yes, basically.
Yeah. So
if the part can run at that speed, the other station, so top camera or side dimensional camera, can do their inspection at their speed. Correct, Gabri?
yeah. So of course.
Don't be shy, so you can make questions.
Obviously, if we don't have any other 360 station, the other part of the question is what is the acceptable first reject rate under this condition? Gabriele, want you explain what happens in the past when we started to work with artificial intelligence about 2 years ago? What was the first results that we see under false rejects?
Yeah. So this machine that you see before was designed especially to check the big damage on the thread. So in this case, the false reject is very low because we found a very big defect, and in this case, the false reject is absolutely lower than 5%. Okay, probably also lower. Obviously, if we try to check very small defect, but this is the same also for other kind of technical, most of the defect is small, and higher is the possibility to have a little bit of false rejects. Normally, the speed in this case do not involve too much the false reject. So if you run at 700 or 300, normally the false reject is mostly the same.
It's more the surface treatment or other condition of the part that can affect the rejection rate. Correct?
Yeah. Yes.
Dirtiness or yes. So do you plan to make such a AI function for internal threads?
Yeah, we made it. We made it also in other kind of machines. So for with the special for the glass dial machine, we use and we plan to use also artificial intelligence for some internal thread. Yeah. Obviously, every time is necessary to check the parts because we never forget that the artificial intelligence can work when the defect is visible. So if you can visible with your eyes, and if if the defect is visible on the camera, we can work on it. Sometimes the challenging is to find a way, for example, for illuminate properly the parts or to see the parts in the better way. But yeah, it is possible to work also in the internal thread.
Yes, to check, for example, damages.
Okay. So maybe Guido said to me that we have a video about internal thread inspection. So we can go ahead with another question, and maybe we come back on the video when it's ready. Okay, sorry, it's ready. No. Okay, so we try it again.
So we have a part, I go forward with the following question. We have a part with a math thread, meaning it has one thread on the body and another on the tip. It is possible to inspect both, correct? If both the area of the thread are inside the visible area of the cameras, yes.
The video now. We have the video now. I hope it works. Want to see something?
Yes, we see, but we don't listen.
Say something.
Okay. Okay. So this is an MCV6. This is a glass dial machine. This is a parts that have a thread inside. So now the video is not so
Yeah, it's
easy
a flange.
to see, but
It is a flanged nuts. So we have inner thread cameras that looks inside the thread.
yeah. Oh, this
So
is
we
another.
yeah.
Okay, so it is a typical thread inspection.
Okay. Anyway, we can have multiple view of the thread and inspect for damages, visible damages also on inner thread. Okay, I think we don't have any other questions here that arise.
Non ti si sente, Guido?
We are perfect in time, so I hope that you enjoy this webinar, and I thank everybody of you for your presence. You will receive an email to give us a feedback about the webinar, if it works or not, if everything is okay. You know that we have another appointment for the 23 October the 23rd, isn't it, Alan? Yes. About artificial intelligence applied to
Crack
control, crack detection. Obviously, if you want to see machines running, you can come in Dimac as you want and when you want, and we are very happy to host you in every situation. Simone, do you want to add something?
No, I want to thank you everybody for joining us. If you want to deepen more the technologies on new machines or existing machines, so don't hesitate to get in touch with us or with your sales team in your country. Okay?
Thank you and goodbye. Good evening.
Thank you all.
Goodbye.
Bye-bye.
Thank you. Thank you. Bye-bye.